This video clip starts in section 3, ILRMA, Independent Low-Rank Matrix Analysis.
In this picture of the tutorial structure, this section is located here, colored in yellow, and in the determined BSS methods, colored in green. If we zoom into the determined BSS again, we have time-varying Gaussian ICA explained in the previous section, and ILMA presented in this section. So what is ILMA, Independent Low-Rank Matrix Analysis? It is an extension of ICA. They are both independent something analysis. In one word, ILMA integrates ICA and NMF, non-negative matrix factorization. More specifically, ILMA incorporates NMF as a source signal model and provides a way to full band source separation. Although NMF is a well-known method, let me spend 5 slides to explain it. Given a matrix X whose elements are all non-negative, NMF factorizes the matrix into smaller matrices T and V whose elements are also non-negative. Here, K is a hyperparameter representing the number of bases in the factorization. This is an example with K equals to 2 bases. As you can see here, the column 1, 1, 0, 0 appear twice in X, and this column constitutes one of the basis vectors. From this kind of factorization results, we understand that NMF performs clustering or frequent pattern extraction. This is another NMF example applied to an audio signal. We have the spectrograms of this sound. Let me play back the sound. NMF produces 2 matrices shown in the right. In the T matrix, we have extracted frequent sound patterns. In the V matrix, we have the timing information that represents when each sound pattern begins and attenuates as time goes on. For an intuitive demonstration, let me synthesize a sound made by 3 NMF bases. This sounds like this. From this example, you can intuitively understand what NMF does. An algorithm for NMF minimizes the divergence between the given matrix X and the product of factored matrices T and V. Let's call the product H because this corresponds to the time-varying variance explained in the previous section. The total divergence, denoted by uppercase D, is defined as the summation of the element-wise divergence, denoted by lowercase d. And for the element-wise divergence, 3 types of divergences shown here are well known. Among them, we particularly employ Itaklasaito IS divergence because it has a strong connection to the time-varying Gaussian distribution explained in the previous section. By eliminating some constant terms from the divergence, we can define the cost function of NMF with the IS divergence. And to minimize this cost function, multiplicative update MU rules are known as shown here. A nice thing about these rules is that once the parameters t and v are initialized with non-negative values, the update rules keep them non-negative because these square root terms are always non-negative. Now let's apply NMF to a speech source. Let me play back the sound. EUSIPCO is the flagship conference of EURASIP and offers a comprehensive technical program addressing all the latest developments. This is me speaking one of the scripts, and the spectrogram looks like this. Applying NMF to this speech source, we have this result with 10 bases. From this NMF result, we can reconstruct the speech, and it sounds like this.
EUSIPCO is a flagship conference of EURASIP and offers a comprehensive technical program addressing all the latest developments.
As you hear, the sound is not very clean, but at the same time, we can roughly recognize when and in what frequency the speech is active. We implemented an IPython notebook code and also a Python code for NMF and some utility functions applying STFT. Let me execute these codes. First, I read NumPy and SciPy.io and also Matplotlib, and also my NMF code. It's less than 50 lines of code, and also some utility functions applying short-time Fourier transform and inverse of them, and also writing some wave file. So let me execute the first block of line, and then I read recorded sound here and plot the sound. Then I apply STFT to the sound file, and we get spectrogram like this. Then we apply NMF with the number of bases 10. And the number of iterations for NMF optimization is 30. And this figure shows a convergence. Then I plot the NMF result. This is T matrix representing 10 bases, 10 frequent sound patterns. And this is V matrix representing the timing of each sound patterns. This is the reconstructed speech. It's not very clean, but you can hear when and in what frequency the sound has a power. Here we define a function to reconstruct the sound with phase information, and we can reconstruct a time domain wave file from the NMF result and also the phase information from the original sound. Now we come back to ICA, but this time we consider full band source separation. We have two sources here, and they are mixed by the mixing matrices defined for frequency bins. What we want to do is to separate these two-channel mixed signals X into the source estimates Y by multiplying separation matrices in frequency bins. However, ICA executions for frequency bins would not get to full band source separation because of the order indeterminacy of ICA, and this is called the permutation problem. There are many ways proposed for solving the permutation problem. Among them, introducing a full band source model is one way to the problem. The topic of this section is ILRMA, and it employs NMF as a full band source model. As alluded at the beginning of this section, ILRMA integrates ICA and NMF. This slide intuitively shows how ILRMA integrates them. First, we apply ICA to each frequency bin and obtain separated signals. However, at this point, they are not well separated because of the permutation problem. Then, we apply NMF for each of the separated signals and obtain a row-rank representation for each signal. These row-rank representations are then used as time-varying variances for time-varying ICA. By iterating these loops for several 10 times, we hopefully obtain clear separated signals, and they can be regarded as independent row-rank matrices. The name ILMA comes from this result. Let me spend 2 slides to explain the mathematical aspects of ILMA. This slide explains the cost function. Regarding the ICA part, we have to estimate a separation matrix W for each frequency bin I, and separated signals Y are calculated as shown here. Then the power spectrogram of the separated signal is modeled by NMF. So matrices T and V, or the product H, are the parameter to be estimated in the NMF part. Here, the detailed derivations are omitted, but the cost function of ILMA is given by this formula. This red part is exactly the same as the NMF cost function for each source, N, and relevant to updating T and V matrices. This blue part corresponds to time-varying Gaussian ICA explained in the previous section, and relevant to updating the separation matrices W for frequency bins. So also from the aspects of the cost function, ILMA integrates ICA and NMF. This slide shows the Irma algorithm. Basically, we iterate the ICA part and the NMF part until convergence. Regarding the ICA part by IP, iterative projection, the only difference from the previous section is the calculation of H, time-varying variance, which are calculated here from the NMF result using T and V. Regarding the NMF part by MU, multiplicative updates, the difference from the original NMF is that the target matrix is not the observation, but the separated signals, which are calculated from the ICA result. Now let's separate the two source mixtures that we recorded on our own. The video of the recording situation was played back in the introduction. Let me play back the sound mixtures recorded by the two microphones on the IC recorder.
We are demonstrating blind source separation for convoluted mixtures of speech in a real room with real talkers.
As you hear, the two persons' voices were mixed. Then we employed Ilma to separate the mixture and obtained two separated signals. The first one sounds like this.
EUSIPCO is the flagship conference of EURASIP, addressing all the latest development in signal processing.
The male's voice was successfully extracted. The second one sounds like this.
We are demonstrating blind source separation for convoluted mixtures of speech in a real room with real talkers.
You may notice some residual interferences, but basically the female's voice was extracted. This graph shows how the cost function of Ilma was minimized as the iteration went on. You can see that 50 iterations were enough to get a convergence and the separated signals. We implemented IPython notebook code for Ilma. First, I read some libraries from SciPy, Matplotlib, and Time, and also Ilma Python code, which is like this. It's just 100 lines of code. Then I read speech mixtures file, and it looks like this. Then I specify the FFT size and frame shift for short-time Fourier transform. And then I execute Ilma with the number of iterations is 50 for two sources. It took about 5 seconds for maybe 8 seconds of speech. The separated result looks like this. And this plot shows how the cost function of Ilma is minimized. This is the last slide of this section explaining Ilma and summarizes the key concepts introduced in this section and should be carried over to the next sections. The first one is NMF, which can be used as a full-band source model. And there exists an efficient algorithm based on multiplicative updates. The second one is the full-band extension of a narrow-band method. In this section, a narrow-band method, ICA, is extended to ILMA by combining NMF. In section 7, more methods are combined with NMF for full-band extensions. This is the end of section 3.
This is section 4 of our tutorial. The section title is Rank 1 Spatial Covariance Analysis, R1CA. In previous sections, we treated determined BSS method. They are applicable to the determined case where there are as many sources as microphones. In this case, source separation can be performed by applying the separation matrix to mixtures. The separation matrix can be estimated by time-varying Gaussian ICA or ILMA. From this section, we switch to underdetermined BSS methods. They are even applicable to the underdetermined case where there are more sources than microphones. In this case, source separation cannot be performed by just applying the separation matrix, and so we need a multi-channel Wiener filter. In this section, we introduce a method for underdetermined BSS proposed by Cardoso and others in 2002. We call it R1CA. It is of significant importance because all the other methods for underdetermined BSS treated in this tutorial can be considered as its extensions. This is the processing flow of R1CA. As I said earlier, in underdetermined BSS, we need to design the multi-channel Wiener filter. Once this filter has been designed properly, source signals can be estimated from the mixtures. To design the multi-channel Wiener filter, we need to know parameters of source signals, such as power spectra and mixing vectors. Since these parameters are not given a priori in a blind setting, they must be estimated from the mixtures. This section is structured as follows. We first describe our signal model in section 4.1. Then we will describe the multi-channel Wiener filter for estimating the source signals in section 4.2. Finally, we will describe estimating signal parameters in section 4.3. So now we describe the signal model. This slide compares the signal model in ICA and that in R1CA. FastFCA estimates the separation matrix modeling the inverse system of the mixing system. This makes ICA inapplicable to underdetermined case, where the separation matrix is not well defined. In contrast, R1CA directly estimates the mixing matrix modeling the original mixing system, and this makes this method applicable even to the underdetermined case. Moreover, a noise term is introduced to deal with background noise. So, the signal model here is given as shown here, which is an expression using the mixing matrix capital A. In this section, we omit the frequency bin index I, as in previous sections, because R1CA operates on individual frequency bins independently. There is another important expression which uses the mixing vectors A. The mixing vector is composed of the transfer function from a source to all microphones. The mixing vector for source n is denoted by AN, and nothing but the nth column of the mixing matrix. Using the mixing vectors, the signal model can be rewritten as shown here. Here, each term in the summation is the contribution of a source signal to the mixtures and called a source image. Now we describe a stochastic signal model. The source signals are modeled in the same manner as in time-varying Gaussian ICA. That is, the joint distribution of all source signals decomposes into the product of the marginal distributions of the individual source signals, as in this equation. Each marginal distribution is modeled by a complex Gaussian distribution with a time-varying variance h. On the other hand, the noise is modeled by a multivariate complex Gaussian distribution described by this probability density function. Here, capital B denotes the noise covariance matrix. Actually, we see the distribution of the source signals can also be rewritten using the multivariate complex Gaussian distribution like this. Here, H denotes this diagonal matrix. Moreover, we assume that the source signals S and noise B are mutually independent. Here we show a simulation example. We generated mixtures according to a signal model by running a Python script rank 1 mixtures I pi and B, which is available to you. So I encourage you to play with it yourself if you are interested. From the figures, we see each source image lied on a line parallel to the mixing vector. On the other hand, the noise was distributed in a more isotropic manner. Consequently, the mixtures, which are the sum of the source images and the noise, looked like this. Now we move on to section 4.2, Multichannel Wiener filter. The multi-channel Wiener filter is a multi-channel extension of the well-known Wiener filter. Suppose we are given multi-channel data X, which are a complex-valued stochastic vector of dimension dx. Denote by U an unknown variable to be estimated, which is a complex-valued stochastic vector of dimension du. Now, we'd like to design an estimator of U of this form, which is a linear function of the data X. Here, coefficient matrix F is assumed to be deterministic. Different choices of the matrix F lead to different estimators, but what we'd like to do here is find the one that minimizes the mean square error between the unknown variable U and its estimate U hat. The solution is given by this equation, where the first term is the cross-correlation matrix of U and X, and the second, the inverse of the autocorrelation matrix of X. This optimal filter is called the multi-channel Wiener filter, also known as the linear minimum mean square error estimator, or the LMMSE estimator for short. Now we apply the multi-channel Wiener filter to our BSS problem. The data X are now the mixtures X. The unknown variable U is now the source signals S. X and S are related to each other by this signal model. The covariance matrix of S is H. The covariance matrix of noise is B. Since S and B are mutually independent, the cross-correlation matrix is 0. Consequently, the source signal estimate by the multi-channel Wiener filter becomes like this. A challenge in designing this filter lies in that the parameters A, H, and B are unknown and so need to be estimated from the mixtures. Now we move on to section 4.3, Signal Parameter Estimation. Here we estimate the parameters by the maximum likelihood method. Based on the signal model shown here, the mixtures X have this complex Gaussian distribution. This can also be rewritten like this, using the mixing vectors A. Let us denote the covariance matrix by capital X. In the maximal likelihood method, the parameters are estimated by maximizing the log likelihood, which becomes like this. Maximal likelihood estimation can be performed by the expectation maximization algorithm, or the EM algorithm for short. It uses auxiliary variables called latent variables, denoted by Z, and a surrogate function called a Q function, denoted by Q. It alternates an E step and an M step. The E step updates the posterior distribution of the latent variable Z given the data X based on the parameter estimate theta prime at the previous iteration. The M step updates the parameter theta so that the Q function increases, where the Q function is given by this equation. The EM algorithm has many advantages. For example, it is guaranteed that the log likelihood is non-decreasing. Moreover, there is no need for tuning the learning rate, unlike in gradient method. In our case, the latent variable Z consists of the source signals S, and the data X consists of the mixtures X. The E-step updates posterior distribution of Z given X, which is given by this equation because of the Bayes theorem. Please note here that in this slide, the prime, meaning parameter estimate at the previous iteration, is omitted for simplicity. This is not confusing because all parameters in this slide are those estimated at the previous iteration. To compute the posterior distribution, we need the prior distribution and the likelihood. The prior distribution decomposes as shown here on the assumption of sample independence. By using this model, the prior distribution can be rewritten like this. As for the likelihood, it also decomposes like this. By using these equations, the likelihood can be rewritten like this. Consequently, although we omit the details, the posterior distribution turns out to be a Gaussian distribution shown here, where the mean mu and the covariance matrix sigma are given by these equations. After all, the E step boils down to updating mu and sigma. The M step uses a Q function defined by this equation. To calculate this, we need the posterior distribution shown in red and the joint distribution shown in green. Please note that we have already computed the posterior distribution in the E step, as shown here. As for the joint distribution, it decomposes into the product of the prior distribution and the likelihood, as shown here. Please note that in the previous slide, we've already derived them as in these equations. So, the joint distribution can be rewritten like this. Therefore, although we omit the details, the Q function becomes as in this equation. By partial differentiation of this Q function, we obtain parameter update rules in the M step. This slide shows the pseudocode of the resulting EM algorithm. Although applicable even to the underdetermined case, FastFCA has drawbacks. In this method, massive numbers of metric operations are required in the EM algorithm. This is because metric inversion is required at each time frequency point and each EM iteration. We can see this by looking at this update rule for sigma, where the frequency bin index I is made explicit. Indeed, the matrix to be inverted in the parentheses depends on both the time and the frequency. Since the number of time frequency points is normally huge, this results in numerous matrix inversions. For example, let us consider a typical case of 8-second mixtures sampled at 16 kHz and SDFT with a frame length of 64 milliseconds and a shift of 32 milliseconds. This results in as much as over 120,000 time frequency points. Another limitation of FastFCA is that it cannot deal with reverberation effectively.